Hello, everyone. Welcome. We're here for another edition of Speakeasy JS. I'm Faraz, and we have here all of our panelists for this week, as well as the speakers who are going to be sharing their talks with us. So, I don't know, everyone just say hi or say whatever you want. Go around maybe. Hello. Yeah, cool. We have Andrew, Paul, Rod, Michael, and our guests for today, Rod and Brian. So, okay, so first up, we're going to do Rod's talk. Rod is going to be speaking to us about some of the stuff. Well, actually, it's kind of I think it's going to be an introduction to content-addressed distributed data structures. But he's been working at Protocol Labs recently on IPLD and a whole bunch of interesting peer-to-peer primitives. So I'm really glad that he's doing this talk and going to be giving us all a good schooling on this kind of stuff. So go ahead, Rod, take it away.
Yeah, so my mic is working, I assume. Yep, all good. Okay, so what I'm doing today is there's a bunch of things I thought I could talk about, but they all feel like they need background because they just jump straight into this whole idea of content address storage, content addressing of data. And I just don't think that that's a generally understood concept in our industry like it should be. So I figure the best way to deal with that is to back right up to the beginning and just talk about the basics. And I know a lot of people in here, this is going to be really basic stuff. This is nothing fancy. This is not mad science. This is really basic stuff. So I'm just trying to cover some introductory stuff, but yeah, I'd love to get some feedback as we go. If there's questions coming in, feel free to interrupt me for us if they come in live, or anyone else who's watching in the room. But yeah, let's get into it and look at content addressing and data structures and how these things fit together. Okay, content addressing. What is it? Well, the content addressing basically means the address of a piece of content is derived from the content itself. And it's typically a hash digest. So you take the content, which is some random array of bytes, whatever it could be. It could be text or it could be something else, video. You run it through a hash function, and from that you derive your address. So common examples of that, we're all used to Git. Git is a SHA-1 of a change set to your repository. And so the Git commit address, or the hash, is this SHA-1. In Bitcoin, the hash function used is a double SHA-2 over the 80-byte header of a Bitcoin block. So we're used to seeing these Bitcoin hashes thrown around. That's what that is. So that's the address, and the content is this other thing that you can refer to. So why would you do that? So there's a number of reasons, and the main ones are, first of all, it's secure, because what it gives you is authentication, automatic authentication built into the addressing. So the address authenticates the content. So therefore I can trust, I don't even need to trust you if you're giving me the content that I've asked for by the address. If I say I've got this hash and it addresses a Bitcoin block, can you give me the data? If I know how to run the hash function, then I can authenticate the data is what I asked for. So you get this free authentication that comes with it. It's immutable, can't change. I don't have to worry that I've got a news website and I give the address to someone else to have a look at some news article, and they go there and the news article is completely changed. I know that the address will always give the same thing, and if I need to refer to a new version of it, I need a new address. And the other thing that's a little bit more subtle is you get deduplication. So because the hash function will output the same address for the same data, there's a lot of places where you get to say, I don't need to store or refer to this same thing again because I already have it, or it's the same as something that already exists. I won't go into that more, but it might come out in some of the later discussion. Another term that you hear in this space is Merkle trees. The Merkle trees comes from the guy that coined it, Ralph Merkle. It came from a patent in 1979. And a Merkle tree basically says that the content being hashed may also contain hash digests of other content. So therefore, any content address which authenticates content which is it automatically authenticates content which is linked via the inclusion of their digest in the tree below it. So if you look at the little figure from the patent, you'll see down the bottom you've got some raw data, then you're hashing chunks of it, and then you're appending hash digests together and then hashing those and passing that all the way up in this binary tree to the top where you've got one hash. And then that hash authenticates each of those chunks individually as being part of the hash. Now, Merkle trees are also known as authentication trees, hash trees, and you'll see later that this extends all the way to the concept of a blockchain. It's important to note here that a Merkle tree doesn't strictly refer to this appending of hashes together. A Merkle tree is simply the inclusion of a hash in some data. So it's just by linking to including a hash in your content and then hashing that, you're creating a Merkle tree. So they don't have to be this strict binary form. They don't have to be just include hashes in these intermediate nodes. But you will often see this pattern as we'll get into some examples. Another term, and this came up a few weeks ago when Michael did his talk on ZDAG, his block format. DAG, directed acyclic graph. This is directly from graph theory. It's not specifically about content addressing, but we apply it. What it means is a DAG is directed, which means that the linkages between the nodes flow in a particular direction. So in non-directed graphs, there's no directionality to the linkages, but in a DAG, there's a directionality. And acyclic means that there can be no cycles in the graph. So the linkages flow one way, and there's no loops. And we can see that a Merkle tree, or these Merkle structures, they're DAGs because a hash function is directional. You can't reverse a hashed function. That's one of the points of them. So the hash of the data points to the data. There's a directionality. And there's no cycles. You can't link to content that doesn't already exist. So you can't create a hash for something that you don't already have. So there's this time component to it as well. So a Merkle tree is sometimes called a Merkle DAG. These terms are often mixed up together. Let's look at how you might use this practically. A good example is that you'll see in the wild a lot is file systems, and this is you'll see this in IPFS, and I'll show you another example straight after this as well of where it's used. But let's say we want to build a file system of distributed chunks, and let's say my files are these distributed pieces, and I've got 8 files here, and I hash all of the files, and I get the little addresses for them. Then I include those addresses, these little hash digests, in these directory chunks, and the directory might contain names of files. It might contain the name of the directory itself. Whatever it is, it's just some kind of blob of data that has those hashes in it, as well as some other metadata that identifies as a directory. And in this example, I've got a directory 1 is pointing to directory 2, which is also pointing to files. So I've got a multi-level directory structure here. So everything in this graph gets a address or a link. So there's 10 pieces here. There's 8 files and 2 directories. And you can point to any of them individually as well. You don't just have to point to the directories. You could just pull out a file and you've got a link to that as well, because they've all got their own addresses. Here's one way where that structure is used. It's used in Git. And Git adds this extra layer of these commits above it. These commits are data structures that it layers on top of files. So, and Git is a Merkle DAG as well. It's got the same things going on. It uses SHA-1 addresses, and everything in here has a SHA-1. This is a very simplified version of Git, by the way. But down the bottom, we've got these blobs, which are generally files in our Git repository. And they bubble up into trees. And trees can also point to other trees. Then you get your directory structure, essentially. And then the trees, those things are hashed as well, and they put into these commits, where we get our little commit strings from. And the commit contains the author, the committer, timestamps, the message, and then it points to the tree data, but it also points to this parent, which is the previous commit that you're building on top of. So you build this directional graph, and everything's hashed, so it's Merkle DAG. And in this example, starting from the right-hand side, That's an original commit. There's 4 files in just a plain Git repo. Next commit introduces 2 more files, but it still refers to the original 4. Then the next commit introduces a directory structure. It removes files, it adds new ones, and it makes the Git repository more complicated. But each of ththese things, again, has their own SHA-1 address. This is a Merkle DAG, there's directionality. This is what we're talking about with content addressing. Another example is a blockchain. Bitcoin in particular is an easy one to talk about because it's so many blockchains are just forks of this code and they use the same structure. Ethereum's a different beast and some of the newer blockchains are as well, but this is a simplified version of Bitcoin. When Bitcoin refers to a block, they actually refer to this data structure that contains multiple independently hashed things. The thing where you have a Bitcoin block address is actually the hash of a header, 80 bytes of header. In that header, there's a hash inclusion that points to this thing called a TX Merkle root, and that is this binary Merkle tree, like we saw in the Merkle patent, where it's actually just appending hashes together to form this strict binary tree. And at the leaves of this are hashes that point to the transactions in the thing itself. And the header also points to the previous block, and that's where we get the blockchain from. So the blockchain is actually headers pointing to headers all the way back to the Genesis block. And within the headers themselves, they point to their own transactions. So they're all bundled up. One of the interesting things about Bitcoin is that this binary Merkle tree structure on the side there is actually not included in the bytes that are shipped around between Bitcoin nodes. They only include the transactions. And the reason for that is they can derive that binary Merkle tree to prove that it exists. So the header includes this Merkle root, but if you've got the transactions, you can generate that by regenerating this binary Merkle tree. So still, again, it's a DAG, it's a Merkle tree, same thing. Backing up to our example, the directory one, this concept of a root is really important. A root is a single thing that you can hold on to that points to all of the things that you want. In this case, we've got directory 1 is our root. It points down to these 9 other pieces. And this one reference can refer to an entire graph. We could also choose directory 2 as our one reference. We could hold on to that, and that's all we care about, but then we'd only get the 4 files underneath it. We could create a new one and hold on to that, and maybe that one points to directory 2, doesn't point to directory 1, that's sort of lost to us somewhere else, but we add 2 more files. And we can actually include mutability in this, because now what I said in the beginning that immutability was one of the properties of this, but if you include mutability, you can, well, it's mutability of a sort, and I'll show you what I mean by that. If you hold on to a root that points to your data structure, and you keep this root as the important concept, if you change the root over time, then you get a kind of mutability. So in this example, let's say I want to change file 1. Maybe I edit file 1 and put some new bytes in it, and that changes the hash. That hash then bubbles up to the directory 1 blob, and that needs to change. But if I just create a new directory 1 with a new hash, then I've got a new root, and that points to this new graph where I've got the edited file 1, but the rest are the same. Now, I could also hold on to the original root if I wanted to. And one of the interesting properties of that is that you get these snapshots over time, that I could actually walk back in time if I had access to all of these pieces, these blobs, if they were stored in my store somewhere. Mutability extends to all of the kinds of operations you could do with data structures. Let's say you've got some kind of, maybe this is a B tree data structure, and you've got some predictable layout, and you want to perform some operations on it. The root is the thing I'm hanging on to, and I can navigate from the root to everywhere using some specific algorithm. Let's say I want to add elements here, remove elements, shuffle things around. I can do a bunch of operations, generate a new root, and you can see here I've got snapshotting, so I could walk back in time to the original root. But I've also got the ability to all the operations I mentioned there. I can add things, remove things, and What was I going to say about that? I've forgotten what I was going to say about that. It was an important point there that slipped my mind. But basically, if I've got predictable algorithms I can run across these things, I can mutate these graphs, hold on to the root. I could discard the old root and maybe garbage collect the elements that I don't care about anymore. That really depends on the system I'm working within. So algorithms for working with these things. So this is quite a complex area. Because we're dealing with really complex systems, especially when we're dealing with distributed systems, because the nature of the systems come into play. So how do we choose or design algorithms? Well, we need to ask questions like, is mutability needed? Do we need to be able to mutate this thing over time, or do we just want to create it up front and then ship it to the world? Maybe I have a video file I want to package up into blocks and ship it to the world, and that's all I care about. So maybe mutability is not needed, or maybe it is. Maybe I want to do a distributed package manager. And I want to be able to update it over time. So I need to ship these new routes around all the time. What does that look like? So what other operations do I need to run these things? Traversal. How do I want to get through my graphs? Do I need to do sorted traversal? Do I need to do iteration over the whole lot, or do I just want to go to individual ones? Do I need to do size? Do I need to understand the size of these things? So got to understand the priorities to get to these algorithms. How much data should you fit into a block? These single things that are hashed, then that's going to be very dependent on the system, because the nature of the storage and distribution medium will impact all of these decisions. So maybe I'm using IPFS, and there I've got a recommended maximum size of a meg, but very commonly you'll have much smaller than a meg as well, and you want to ship these pieces around. And the size of the block will impact a whole bunch of other things. This stuff's not new though. So distributed systems, fairly new. But these algorithms are not new at all, because persistent and immutable data structures have been around for quite a long time, and these things have been researched. We find them a lot in functional programming languages and functional programming libraries that you can use in non-functional languages. Standard libraries of Scala, Clojure, Haskell, etc. They're all full of data structures that would translate almost directly into this world. Things like HAMPs fit directly in here, and you can create distributed versions of them using the same algorithms. But the algorithm selection requires careful consideration of all of the trade-offs that I mentioned as well. So there's this whack-a-mole you have to play with. What is the nature of the system I'm using, and what are the kinds of operations I want to perform on it, to figure out what algorithms you want. Am I over time for us? Should I stop here, because I do have an example I wanted to get into?
Yeah, you have time.
Okay, let's. I've got a few slides here just to quickly build out an example. Let's say I want to build a multi-block content address super large array. Now, let's say I've got data that I want it to live in content address land, and this thing could be arbitrarily large. Perhaps it's so large I couldn't fit it in memory in my own computer. Perhaps it's so large I couldn't even fit it on my own disk. So it's going to live out there in this content addressed world, maybe on IPFS. Maybe I'm putting these blocks into S3. Maybe that's all I'm doing, but they're out there somewhere, and I just want to be able to navigate through this array and store things in it. Now, I want it to be generic. The encoding form doesn't matter. This could be JSON, this could be CBOR, this could be ZDAG. As long as I can hash these blocks, I can use hashes as the links, and I can store and load this data with hashes. So if I've got an operation where I can fetch by hash and I can store by hash as well, that's all I care about. Now, the leaf elements in this array, they could be anything. Maybe they're just simple integers. Maybe they're complex objects, or maybe they are hashes themselves. Maybe I want an array of hashes because I'm building NPM. I don't know. So let's just build a super large array algorithm. This is just quickly. Let's start off with a block and define a maximum width. So I know how big these blocks should get up to. And so here I'm using JSON here as illustration. So these blocks are just JSON arrays, and I'm defining a width of about 5, right? So if I store an array of 4 things, I can hash that. That's my root. I have a root that is single block. Great. I can now go into my block, fetch out elements from that block. That's easy. And I can do it up to this maximum width, so up to 5 elements in my little block here. And that's simple case, 1 block. If I mutate that block, remove, add elements, then I get a new root address. But as you can see, if I was to remove element 5 from that second version of the array, then I should actually get back the same hash as the first version. So it's like stepping back in time, even though it performed a removal. So that's one of the nice properties of content addressing. Okay, so let's add more elements. What happens when we add more elements? If we go beyond the fixed width, let's add a new root that refers to an additional block. So overflowing our maximum width says that we have to make a new block to start storing elements in, and that new block can be up to the same width before it overflows. And then each of those blocks gets hashed, and we store those hash addresses in a new root block. And the new root block has the same rules as well. It's got a maximum width as well of 5. So let's call this a height of 2 now. So height at height level 1 are the actual elements. Height level 2 is this root block that has links to the height 1 blocks. Now, if you think about it, you can see that if our height 1 is constrained to 5 elements, then at height 2, we have a maximum capacity in our array of 25 elements, because then we can fit 5 blocks of 5 before we overflow at our height 2 single block. But that's fine, because we can overflow that as well. So there's our maximum capacity height 2 data structure, single root block pointing to 5 different things. If we overflow that by adding a new element, we add a new height. And that new height refers back down to the height number 2. So we've got height 3 here that refers to height 2, which refers to height 1. So at a height of 3, width of 5, we have this new capacity of 125 before we overflow our height. So we can just keep on adding things to this thing, and it goes outwards and upwards. Right, so traversal is interesting. So we want to say we've got this root, we've got this reference to this root, and we want to traverse to index 21. How do we do that? We need an algorithm where we can enter in the root and then figure out where to go at each point in this graph. The algorithm's not too hard, and there's some JavaScript to illustrate it. Basically, what you're doing is you're slicing off bits from the index at each height. And to do that, we can do division and modulo operations. So if we enter, each node needs to know what height it's at, and it needs to know how to get to child elements if it's not at the height 1. So if we have this root and it's height 2, and we say get me index number 21, then we run this little algorithm. It says, okay, I'm not a height 1, so I have child elements. I need to figure out which child element to call into. So you slice off some bits, and you say, I want which child index. You can run this division. I'm not going to go into the details here, but basically I get the index of my child element, and then I get a new index to pass to that child element. So in this example, the child element would be the first element. It's actually 0. And then the new index for that one would actually still be 21, because I'm not slicing off any bits, but I pass into that child element and say, I want you to get me index number 21. But if I was to 26, then it would be a different path. So basically, this is just an algorithm to traverse from the root to any node. And you need more algorithms too. You need things like size. If I want to know how big this thing is, there's an algorithm to get size of it. If I want to delete elements, there's a whole other algorithm there. Just quickly, the properties of this array. This is just an example. This is not. I'm not saying this is an array that would be good to use in every situation. This is an array that might be useful for some situations. But we need to understand what the properties are of the various algorithms in order to judge whether it's useful, and also how to tune it. So we can see that the width means we would have larger blocks and fewer levels, which might be good. Maybe I want to have blocks up to 1 meg, which would mean quite large. But then you can see that mutation could be expensive, because I'm garbage collecting quite large blocks. But then I have fewer levels to navigate. Maybe I've got network latency weighing into this as well. So there's a whole bunch of reasons you might tune that width to suit your environment. Maybe all these blocks are local, so small width is great. The get and size operations are pretty efficient. They just need to traverse down to height 1 single blocks. And you can get the answers to these operations. Appending data is pretty efficient too. It only requires mutating a maximum of 1 node at each level. And there are some cases where you don't even need to do that at some levels. So if you're at the boundary case, you're just adding nodes. Ordered iteration is really simple. It's just a left to right tree traversal. This thing just folds out into a normal tree structure, and you just do left to right traversal, and that's your ordered array iteration. Slicing this array is possible, but it's only efficient if you perform it at the boundaries of your width of your block. So if I was to slice at boundaries of 5, great. If I was to do anything else, then I'm rewriting everything to create a new version of this thing that would fit into the new structure. Prepending data, putting it at the front, is really costly. There's the algorithms to do that. Can work out if you're dealing with width boundaries, but very costly because you end up rewriting everything and mutating the whole structure. Deleting elements other than at the tail is very costly as well because you're shuffling things up, rewriting, mutating data. And lastly, it can't handle sparse data. You'd have lots of blanks and it would be very wasteful. There's a bunch more properties to this. We actually have a spec for this. We call it vector in IPLD. If you go to the IPLD specs repo on GitHub, there's a whole write-up on the various algorithms to traverse and mutate this data structure. Very interesting there. There's JavaScript implementation of it, and there's a Go implementation of it you can have a look at as well if you're interested. But that's all I have. Hopefully that quick example was illustrative, and hopefully I haven't used up too much time.
No, it's all good. Thanks a lot, Rod. That was amazing. I wish we had an applause track or something to play right now because it's not the same in a virtual end of a talk. But yeah, no, I also wish that you went first earlier than all these other talks we had because you really laid out a lot of the basic primitives in a way that makes the other talks easier to understand. I think a lot of times people don't, people can jump into like the more interesting advanced stuff about whatever they've built. And if you're watching a talk like that, it can be really confusing and it can be like, well, am I missing something here? Where's the context? And there's just not enough time in like a 15-minute talk where you're introducing like whatever, Michael is introducing ZDAG and like, you can't also explain what a hash function is and all these other things. So yeah, really great introduction. Thanks for doing that.
That's why I put this together, because I was listening to Michael and also Merkle and the talks about hypercore and all the rest of them. They're all the same sort of things where you sort of need a little bit of background at least. And I know when I started getting into this, I needed all this context. So hopefully that was helpful. Yeah,
totally.
I really like the diagrams. I thought that the color coding them and then being able to go step slide by slide through these similar data structures, I thought was really effective to kind of understand all the similarities. So I really appreciated that.
Yeah. So we don't have any questions right now from the chat. We just had somebody mentioned that it wasn't really a question, but it was more of a comment, that the trick of shifting a root node to another root node whenever you change one of the lower, the leaf nodes, gives you like a fully functional data structure. And so content addressability can really help. And I think you mentioned that a little bit, but that's super cool.
Oh, there's also this whole new field that is really going mad in research area at the moment, research areas, which is these conflict-free data structures. And a lot of those touch on the same kinds of areas because immutability, functional data structures, those things play into the same strengths. So there's tons of research going on for massively parallel computing and distributed computing where this stuff just overlaps.
There was one question in the chat that I thought would be good. They were asking how does index addressing still maintain the properties of the content hash addressing of immutability in this context? Because as you were describing the algorithm, it was an index which you were using. So could you elaborate on that particular question?
Right. So in my example, I was relying on the fact that in the blobs, each of the blocks was storing an array, and I could index a block. So if I load a block, and I use JSON there as the best way to do this, because I think a lot of us think in JSON when we're talking about serialization. Just if I store a JSON array and put that in and say that is my block, and I'm storing that, maybe I put it on S3. If I load that, I can index into that block. And at all of the height 1 elements, those indexes are actual end elements, but I'm still only got indexes of 0 to 5 at every block. And at the other heights, all of my elements are addresses. And so the algorithm really is to say, if I'm coming in at the top and I know the height, how do I modify my index such that I know which element to look up in this level, and then which element to pass on to the next level, because you're really dividing your graph as you traverse down, and you want to know how do I maintain this index so that it gets to the right point. And what you end up with is this fascinating way where the index will change through the navigation, but you as a user don't need to care about that. But the algorithm will take care of changing the index as it goes down through this data structure and it passes on through the nodes. If you're interested in it, look up the spec, because there's some interesting algorithmic properties here.
This is super cool. I'm getting flashbacks to when I took operating systems in college, when you have an inode and it's like an inode number, and you have to like go to the indirectly or doubly indirect block, and then like go to an indirect block, and then finally find where the data is. It sounds like really tricky bit math that you have to like debug to get it right. Yeah.
Well, one of the talks I wanted to give was do a talk on HAMPs, because HAMPs are really fascinating data structures here. And there's so much interesting math and bit shifting that goes on in that. Maybe we'll do a talk on that later, but same kind of thing where you're navigating down and you're mutating these indexes and looking things up. And it's fascinating, simple math going on.
Super cool. I wish we had time for more questions, but we got to move on now to the next talk, which is going to be from Ryan Dahl. And for those of you who don't know, Ryan made Node.js, and now he's working on Deno, and I'm super hyped to hear what he's going to talk about today. So Ryan, go ahead, take it away. Stage is yours. I think you're on mute, though.
Can you hear me now?
Yeah, we can. Cool.
Hello. Hi. So I'm going to switch screens here. Can you guys see this?
Mm-hmm.
Okay. I've just got a laptop, so I can't see anything other than this. Yeah, Michael asked me to give a talk about the security model in Deno. So I just thought I'd give a quick overview and some demos to kind of explain it. I think it's pretty straightforward. But if anybody has any questions, feel free to interrupt me. I guess you have to interrupt me audioly, because this is all I can only see my screen right now. So right, Deno is a runtime for JavaScript. It's a project I reluctantly got into a couple of years ago. When you've worked on Node for as long as I did, you can't help but kind of think about how things could be differently. Yeah, Deno kind of started out as my way of playing around with how we might be able to make a really simple scripting system. Yeah, I like scripting languages a lot. I end up programming most of my days in Rust these days, but it's really nice to be able to just throw down some scripts sometimes. Hack something together, rename some files, and yeah, I'm just really unsatisfied with the state of the world when it comes to scripting languages. Python's okay, but it's not the same thing that works in the web browser, and it's quite slow. And Lua is one indexed, so totally ridiculous. We've got Ruby, but it's ridiculously slow too. And it just seems like JavaScript. I mean, if there's going to be one scripting language in the world, it might as well be JavaScript. Yeah, this is just kind of my attempt to make a little bit of tooling that I could use. Anyway, oh wait, let's see here. Oh God, wait, I have to exit this. Okay, so I'm going to show you some examples here, and we'll talk about the security implications as we go through. So let me just copy this into my command line. So okay, wait, before I do that. So first of all, Deno is a program that can, run on your, it's a command line utility. And what's cool about it is it can actually run like raw URL. So you don't actually have to download anything. Oh my God, where's that? let's open, oh wait. This is a link to the GitHub page, but not the actual source code. Let's grab the actual source code here. So this is a little file. It kind of implements the Unix cat program where you can give it a file name and it prints it out to standard out. So this just kind of like loops through the arguments of the program. So let me just replace that. Oh, Jesus. I'm sorry, guys. Deno run URL. So you might notice here that so let me take out this allow read first of all. So when you run this program, it's supposed to take some arguments. So actually without any arguments, it loops through nothing, and so actually doesn't do anything. Notice how it downloaded this program on the first time it ran, but then didn't do anything after that. That's because it kind of caches things in a secret directory somewhere. And what you're supposed to do is like this cat program can like cat files to standard out, print them to standard out. So let's try to print my EDC password file. And I get an error. It says uncaught, permission denied, read access to EDC password. Run again with allow read flag. So this, starts getting into what Deno's permission model is, and it's a program for your command line, right? It's trying to interact with your system. But JavaScript, the V8 engine that we're using is actually a secure sandbox. Even though we're kind of poking holes in it so that you can open EDC password and kind of interact with your operating system. If we're really careful about it, we can really kind of control access to the system. Kind of in the same way that like the web browser, you can share your camera. You can have the website get access to your video feed, but you have to kind of opt into that, right? So I like this permissions model where you just kind of opt into stuff. And so in order for this program to actually be able to access this file here, it needs allow read. And there we go. It printed out EDC password. This allow read, since we're talking about security stuff in detail, can be limited to kind of a subtree of your file system. So what I could say is like, oh, you can only have access to like /temp, but not /edc. So like this should still fail, I think, because EDC password is not inside temp directory. But if I do something like this, it should work, right? So these flags are kind of dumb, but have some flexibility to them. I shouldn't say dumb. They're not very fine-grained permissions. Okay, so that's kind of example one. Let's look at a second example. So this one is. In this one, I'm using this URL on the Denoland website. Wait, quick side note about this Denoland website and these URLs. So this is some file, whatever. It's called gist.ts. Who knows what it does? And when you go to it on the website, you get this pretty HTML page. But what's really fancy is that when you curl it, you actually get the raw text, and we have kind of a fancy system where it inspects the accept header of the request coming in. So it knows if you're a web browser, and if so, you kind of displays this really nice page, and otherwise it just gives you the raw content. Anyway, digression. So yeah. So this program connects to the gist service, the GitHub gist service, and allows you to put a file up there. So what I'm going to try to do is just my EDC password. Of course, like EDC password, it has like the shadow, whatever. This should be secure. Notice that, we've got the allow read because it's going to need to like read whatever file. So I'm going to pass this thing EDC password again, right? So it needs allow read in order to do that. But we don't just like give out network access willy-nilly here. Network access could, of course, you could read your SSH keys, and then you could send those out in some sort of outbound request. So we don't give network access by default, and in fact, by default you don't get any access at all. So when you run any Deno program without an allow flag, this should be, I'm not sure if I'm willing to bet my life on it, but theoretically this is a secure sandbox. There's no way to break out of this VM, supposedly. If you could, it would be a bug. Let's put it that way. All right, so let me put in these flags here. It needs allow env because I have a personal access token to GitHub, so I can actually post as myself there. Right. So here's the command. Does it look okay? And it doesn't work. It says, oh, I need access to API get. Oh, okay. I have the wrong domain name here, actually. So right, I mentioned earlier that allow read can be targeted to a certain subtree. Allow net can be targeted to a certain host. And I think we actually have kind of subpaths of URLs supported too. But I'm just going to put api.github there. So what I'm saying is like you can do whatever you want network-wise as long as it's always to this server. And just.github.com, not okay. So let's try that. So it's going. Oh, geez. Okay. All right. So that seems to have worked. Great. There's my EDC password. Right. Let's try something slightly more complicated here. So this is a little program that somebody developed, and this thing searches for user. I'm not sure why they built this, to be honest, but it's for searching for usernames on websites. I'm using it just because it's an example of a somewhat non-trivial program. And what you can do is you can run this thing directly here, and I'll just do that. So when you run it, what I'm saying is like you can't access my file system at all. No way, Sherlock. I don't know what the hell you are. But what you can do is you can access the network, and I'm not going to go through I'm too lazy. I can't be bothered to download your CLI TS file or whatever. I just want to try out your program. And what does it say? Fatal error. Username contains invalid characters. Why is that? Okay, insert username. So I'm going to try Rye, which is my typical username. And yeah, this program does something.
Wow, Blogger's still a thing?
Apparently. Yeah. So, I think this is maybe a silly example, but kind of gives you a feel that like we have these kind of installation-free programs available. And I think what's really kind of cool is that this is all done as well as we can. We're trying to stick to web standards here. Why is this? I think this is actually a redirect, and maybe I have to do -L. Right. So I'm just trying to take a look at this file here, and I think if you're familiar with Node, and you guys are all extreme nerds here, so I'm sure you've heard my spiel about Deno before and the imports, but we do use extensions in the import specifiers, in the module specifiers. And obviously you can actually import fully qualified absolute URLs as well. You might notice that this is all TypeScript. Deno has a ton of TypeScript stuff built in. It does, of course, support JavaScript. Good old JavaScript should always work. And, you know, it's kind of a struggle when you support TypeScript to get people to care about JavaScript, but I still care. And we try to make it really, we try to not make it any slower to run JavaScript than if you were just using V8 directly. That is, it's not going through more compilation passes. TypeScript, by the way, so complicated, such a headache. Okay. So anyway, those are my demos. The security flags I demonstrated allow read and allow env and allow net. There's also allow write to the file system. There's allow all if you just don't care, or you're developing, or whatever, you want to run things in Python mode, as I like to call it. Maybe we should just call allow like Python. So allow run is very similar to allow all. It is actually it allows you to start a subprocess. Of course, once you start a subprocess, all security bets are off. Like that subprocess can do anything. Obviously, that we have no control over how subprocesses run. They can access the network, and so allow run and allow. This was actually a long contentious debate about whether these two things should be the same thing. Allow plugin is a new feature that is not well supported yet, but we're kind of developing the ability to have plugins, extension modules, DLLs, whatever you want to call them, compiled things that load in to extend Deno. And there's allow HR time to get around the possibility of kind of Spectre sort of problems. This is pretty academic. You know, Deno is a pretty new piece of software. I'm not like I said, I'm not sure I would bet my life on its security. So you know, it's debatable whether something like that could be exploited. Actually, yeah. Actually, I kind of messed up the order of these talks, so forgive me while I just move this around a little bit. So, yeah, Deno is the security aspect of Deno was built in from the start, and the way I know there's a bunch of Node people in this group, so I'm more or less speaking to you guys. But Deno is organized quite a bit differently than Node was. We don't allow people to just kind of bind V8 willy-nilly, right? You can't just create like kind of objects in C++ and like stick them into the global scope, right? We actually don't allow you to create any objects with the V8 API. There's actually only I'm going to lie a little bit, but let's say there's only two real functions, two real native functions in Deno, and those are kind of send and receive. Basically, what we have done is we've created a really efficient way of sending array buffers back and forth between your JavaScript runtime and Rust. And we use that ability to kind of send array buffers back and forth to implement everything. Everything's done on top of this. Literally everything in Deno is built this way, which is really nice from a security perspective because everything goes through one funnel, right? There's not all of these different entry points that you need to worry about in terms of security. Like we can kind of have security guards in the right places and do all sorts of other stuff. You can do metrics and stuff. We call kind of functions that call. This is some sort of RPC mechanism we call functions that go over this RPC mechanism ops. So open, for example, is an op, or like read dir is an op. And this is modeled very much after the Linux syscall and kind of the POSIX syscall setup. So we have something like file descriptors, which are integers, which refer to things allocated in Rust. Resources. We didn't want to call them file descriptors because we thought that would be confusing. So there's a resource table, and these resources basically correspond to sockets or standard IO or open files, and you basically can reference them while from JavaScript as just a single integer, and use them in these ops that you're calling to reference data that is more complex objects that are stored in Rust. So yeah, in the implementation of these ops is kind of where we have these security checkposts. Deno, the kind of getting away a little bit from the security aspect, but just kind of the general design of it. It's not as monolithic as Node is. There's actually three major components to the system. There's the Deno executable itself, the CLI as we call it. And then there's Deno core, which is you can think of it as a really slimmed down version of Deno. Like if Deno didn't have TypeScript, if Deno didn't have any file system access, if it didn't have any security things, actually all it is this ops system, which is, vaguely our way of taking JavaScript promises and turning them into Rust futures. Like we worked a really long time to kind of make that connection usable. This Deno core actually doesn't even depend on Tokio, so there's no event loop involved with Deno core. All it is kind of an abstract way of A, running JavaScript, and B, basically binding promises in JavaScript to futures in Rust, but without providing any bindings. And then lower level than that is Rusty V8. But V8 is written in C++. We're using Rust. We love Rust. Rust has saved my life. I don't know. Having programmed C++ for many years, all I can say is that Rust is fabulous, and I will never start a new project in C++ again. Anyway, we had to bind this V8 library, the C++ library, to Rust, and this is very non-trivial, very, very non-trivial. It's a very large C++ API. It's millions of lines of code. It takes an hour to compile, and what we've done is put a lot of work into providing a Rust interface that is zero overhead. So you're actually like handling the exact sort of pointers that you do, like literally zero overhead to what you do in C++. You're literally, the machine code that you generate should be exactly the same as the equivalent C++ code. But we do provide Rust has more type system stuff and can kind of specify interfaces more in a more detailed and precise way. And we're trying to provide, we basically are, I wouldn't say we're 100% there, but we're 98 the way there towards providing kind of a safe interface to this very complex system. Hard to overstate the fact that V8 is a very complex system. By the way, please interrupt me if I'm, I have to check my time here. Okay. Let me just give you guys just a brief overview of some of the other things that it can do. So, we have all of these parsers and stuff built into Deno. So what we can do is, for example, given a URL, we can parse out documentation like this. And you might notice it happens very fast. Yes. All of our parsers are written in Rust, and we use this stuff in our website to provide documentation to any, provide a URL to any JavaScript file, any ES module JavaScript file, stick it into this box, and we should be able to generate some documentation for you. So that's built into the command line. We also have a formatter, very much like Prettier, but 100 times faster, I believe, 1,000 times faster, possibly. We have lint. We've just achieved compatibility with ESLint's recommended TypeScript rules. Also, I believe 100x faster, possibly 1,000x faster, much, much, much faster than ESLint. You will think that it's not running. It has run. It's just written in Rust. We have kind of a test system built in, and we have kind of coverage. Maybe this is worthwhile showing you briefly. If I go into the Deno directory, we have, I'll just show you, there's kind of a node compatibility layer that we have. If you have some code that is requiring FS or whatever, and you want to run it in Deno, we have a layer to do that. But let's just show what it looks like to run the test with coverage on this directory. So I'm just going to run Deno test. It runs through all of the tests in there, and then it prints out some code coverage stuff at the end here. So it tells us which of our code bits need to be worked on a bit more. So yeah, we're kind of interested in making this scripting language very useful, and that means kind of adding tooling. I'm going to stop there. I've got all these other slides, but I feel like I've gone over time already. So, maybe I'll just leave it there.
Cool. Well, thanks a lot, Ryan. That was amazing. I just want to say you're a pretty bold person to be playing with your Etsy password file on a live stream. Yeah, I know that it's not the shadow, but still.
Yeah, it's shadowed. I think that was all solved in the early 2000s. So, yeah.
That's funny. I just had a couple questions that came to my mind while you were speaking. I'm curious, when you said that the files are cached the first time you go to fetch a script, are you actually on later runs doing a check with the server for if it's been modified, or looking for e-tags or something like that?
We don't do that. We cache it forever. So the idea is that when you run it, it's kind of like npm installing something, where it's kind of cached forever. What we have is a reload flag, which is supposed to be like the web browser reload, and that will allow you to re-download those things if you want to do that.
Okay, interesting. That sounds like a good opportunity for if you wanted to be really careful about what you reload. You might even have a way to look at each changed file and look at a diff between what's in the cache and what it currently is, and go file by file for something really security sensitive. That's an interesting opportunity.
Yeah, we might do e-tag stuff. I'm not sure actually, but yeah, the idea is that sometimes you're on an airplane, and obviously we can't expect these URLs to always work, but you should be able to just because we're using a URL doesn't mean that we go and visit it every time. It's just it's a module specifier.
Right.
For whatever's in the same way that the express string is a module specifier for express on npm, right? I mean, it still corresponds to a URL and stuff. It's just you're expected to run this command beforehand.
Interesting. So one other question that I was wondering, when people post their scripts to the internet and they tell people, hey, run this in Deno, do they usually provide the flags that they recommend you run it with, or do you just sort of try, you run it and it fails, and then you try adding what's necessary as you go?
Usually people provide the flags. Yeah.
Okay, interesting. Yeah, I'm wondering if there's any way to express up front and almost like a manifest or a comment at the top of the file, these are the perms that we need, and then the CLI could not give them until the user hits Y or something on each of them.
Right. Yeah, we we actually had a system like that early on, and kind of went back to this kind of throwing behavior just because it was just a bit too buggy, and there's a lot of situations where you want things to kind of just fail. I think we actually have that prompting ability still in there. I'm not sure how to turn it on though. Maybe it's gone at this point. But
interesting. Huh. And then one other question that someone DM'd me privately was they were wondering if I wanted to say install something like Lodash or whatever, some utility thing, and I don't want to give it any permissions, but want my app to be able to talk to the network. Is there any way to do like an import level permission where I just give the package different packages different permissions?
There is not. It's been a much heated topic of debate. I think everybody agrees this would be fabulous and like totally something that we could do, but it's really tricky. I think I guess I'm not convinced that it can't be done, but I'm also not convinced that it can be done securely. So I'm kind of waiting for somebody to do this research. If this is actually possible to do securely, we would totally do it. But I'm kind of skeptical. Like there's a lot of monkey patching and holes that you can do in JavaScript. So
right. So
usability would be pretty awkward too, wouldn't it? Like you need a big manifest or huge command line strings, and quickly.
It's really interesting though. So is the JavaScript language the primary difficulty here? It's just too dynamic and too unpredictable to scope things correctly to a specific import?
Yes. JavaScript is very dynamic. It's really scary to say that for us to make the claim that like, okay, this module that you've loaded over there, you can rely, it can never make network access. And it's just like, yeah, I mean, but the rest of your program can somehow, like in the same address space, in the same isolate. Like,
right.
That sounds like that. Yeah. I would love to be convinced of that this was possible. I'm not really convinced of that. Yeah.
Right.
Kind of a similar question about that. I know if you have a child process, that can easily doesn't have to obey the restrictions, so you need to have allow run. But is there any possibility of adding like a sub Deno that you can pass capabilities into from the parent? I don't know if capabilities are accessible programmatically, but are they?
I mean, you can start web workers, and so you can kind of downgrade your capabilities and start web workers with fewer permissions than you started with. So that can be a way of sandboxing some code. But that's another isolate. Like that's running in a separate thread, not like in your actual in your current isolate. Yeah.
Gotcha.
I know TypeScript has been a little bit controversial in Deno. Well, I don't know if it's actually controversial, but there's been some churn with regard to TypeScript. I'm wondering if you could talk about your opinions on TypeScript for a sufficiently complex project, and are you happy with it? Would you still use TypeScript if you were to do this again?
I mean, I love TypeScript as a user. I think we all do, right? I mean, it definitely allows you to make more complex JavaScript programs, and at a certain point, I love JavaScript too because I'm somebody who just wants to like mash my keyboard sometimes and get something done. But projects grow beyond a single file and get complicated, and I think the TypeScript has proven really useful at that level. I mean, generally, I'd say it's good. The interacting with, we're taking two big compilers, TSC and V8, and we're like smashing them together. And in like that impact zone that's happening there is a lot of late nights for myself, trying to get that all to work smoothly together. And TSC is V8's very fast, TSC very slow. So there's kind of technical problems like that. Like just the fact that TSC is so slow. But I do kind of think that if I did Deno again, which I wouldn't, obviously, but if it was like a couple of years ago, and I was thinking about starting this project. I think there's enough work to be done just on the JavaScript side, and that the TypeScript side of stuff could have been done on top of this, and it might have been a bit cleaner that way. But yeah, anyway, I mean, I think what's really nice is that all of our like standard library and the ecosystem that has kind of come out of this is all in TypeScript. And so we have a really nice code base, you know, where like everybody's very careful with what they're putting out there, and, you know, everything's linted and stuff. And so, yeah, I think it's been a good thing. It's a lot of complexity.
Mm-hmm.
This is winding back, but I had to double check my sources before I commented on this. On the question of module security, there's been some discussion about a secure module spec, which I think in TC39 is under the header of realms. And the conversation around that has not actually been showing positive signs lately. Dominic Deno recently was commenting on the process boundary is the only place that you can effectively enforce security, so that an idea of having any kind of security isolation of individual modules without leveraging process barriers may not end up being feasible in any environment.
Yeah. So, you know, I hear stuff like this, and it's just like, okay, you know, it's not something that we can like, you know, ship out to people immediately. Like, there's still research going on. Like, who knows? Maybe it's possible. But yeah. That's not really the level we work at. We're just trying to take V8 and ship something useful, and kind of the security, the allow read, allow write stuff are just like really easy things we can do to just kind of improve productivity of users. It's just like really nice to be able to run a script and just say like, hey, you only have network access, and that's it, right? Or you can't access my environmental variables. Yeah. I hope that
we have somebody in the chat claiming they work on SDS. So Chris Kowal, if you have more to add to this, feel free to dump that in there.
Oh, Chris, hi. He's been working on this forever too.
So I think Dominic Tarr had a question. I don't know if he has some lag or something. So maybe I'll just ask it for him. Or do you want to go for it, Dominic? Yeah, there's lag.
And I don't think your mic is on, Dominic.
Dominic's in Hawaii, I assume.
On a sailboat in New Zealand.
Oh, yeah, right.
Okay, I'm just going to ask it. I don't know if his audio is working. So he's asking, if Rust is so fast, why write a JS runtime with it instead of like a scripting language that compiles to Rust?
We don't have a scripting language that compiles to Rust. This is just V8, right? So maybe a way to restate that question is like, if Rust is so great, why use JavaScript at all? That's something I ask myself quite a bit. I'll tell you a couple of things. One, Rust is fucking hard, so hard. Like, oh my God, it's very painful and slow to work in Rust. I love it, but very not something that you just hammer out like you know, like, oh, you know, I'm going to take like some AWS API, I'm going to smash it into MongoDB and then do this. Like, no, it doesn't work that way. Like, it, you know, very precise, and sometimes you don't want to be precise when you're programming. Sometimes you want to be fast and sloppy, and I think that dynamic languages are really useful for that. There's times when you just do not care what the runtime cost is at all, right? You don't care. You know, you're writing a database, like you care a lot what the runtime costs are. Like you should be spending that time to write that in Rust. If you're writing a runtime like I am, you should also be spending some time to figure out how to write that in Rust. But if you're writing, what was it, Sherlock, the CLI program that like, you know, prints out people's usernames on different social networks, like nobody cares. Just do this as fast as possible, right? And so this is trying to be a system for doing things when you just want to go fast. And I think that there's a lot of use cases where that's appropriate.
Totally.
I apologize if you covered this already, but does Deno have? Or it looks like Dominic's actually got to go this time.
Okay.
Later, Dominic.
Bye, Dominic.
Does Deno have a native module system?
Yes, it's called plugins. It's not very. We're kind of going more for web API. We're trying to be as close to web APIs as possible, and so we're more focused on kind of adding things built into the runtime rather than kind of extending the runtime. But yes, this is a thing.
And with the web runtime target, I mean, you're looking for orthogonality, right? You want to be able to, is that the word that people are using for that? Being able to run a web script in the Deno environment without having to modify the code, like no browserify stuff.
Mm-hmm. I forget the word they use. Isomorphic?
Isomorphic, that was the word.
Yes.
Yeah.
Some
sure.
mathematical
Why not?
Yeah, that's the goal. I mean, we try as hard as possible, even though like a lot of these web APIs are totally ridiculous. Like fetch is not the best way to write fetch. Is not the most ideal API, but we implement it anyways with just because, I mean, nobody cares. You just want to use fetch. Like nobody cares about the exact details of how streams are implemented. So yeah, at great pain, we implement web APIs, even though we disagree with most of them.
Well, having done that, and then also having worked with Node, how do you feel about the web APIs comparatively? I mean, other than the chore of getting them implemented in the first place.
I mean, some are hit and miss. I mean, I think array buffers is pretty good. I think fetch is pretty good. I think the whole streams thing was a big failure. I mean, I don't know enough about it actually, but it's vastly overcomplicated in my mind.
But if Dominic was still here, he'd probably have something to say about that. He's done like 5 different streams implementations at this point.
Right.
JS cannot win when it comes to streams. We're cursed on the streams.
Yeah, I mean, I think in many ways this is my fault for the initial implementation of TCP sockets in Node, which had a buffered setup. So you can write to TCP streams, and it buffers them up in process, and that's not how the syscall interface is, right? At some point you get like, oh, try again. The kernel buffer is full. We can't write to this again. So there was that mistake, and then the reading mistake was that we had this kind of data event on TCP sockets that just kind of bubbled up whenever you had new data. So by default, the TCP stream was just kind of like iterating reading constantly on new data, and then you could pause if you didn't want to receive new data. This is totally wrong. This was a major mistake in the design of Node's TCP sockets. It's really useful and very obvious once you have async await that you should ask the operating system when you want to read from a socket, right? You should say read, and then you can await it. All sorts of problems happen from this design, and even though it was done in TCP sockets, I think a lot of other systems in Node ended up inheriting this, and there's just been kind of a lot of confusion because of this design choice that was supposed to make things easier, but ultimately did not do that.
Well, in your defense, they didn't have async await at the time, so
that's true.
The design was sensible for the time.
Yeah. Go ahead.
I mean, not in my defense, I would say it would have been better to just stick with the POSIX syscalls and not try to invent that. It was a conscious decision to deviate from kind of the POSIX socket semantics, and because I found them hard. I found it really hard to deal with that, that was a mistake.
Well, I mean, the POSIX syscalls are hard to use as a user. They're like they require like writing loops to like retry around them and stuff like that. Um, yeah, but so are you saying that like maybe the alternative would have been to just expose them as is and then just leave it to like userland to figure out a way to wrap it in a nice way, and then it wouldn't have like forced the ecosystem to adopt the design that you came up with?
Yeah. So
Okay.
so like buffered writes are something that you could have done on top of a write interface that didn't always succeed, for example, right? And this is what we've done in Deno. Not that anybody cares, but if you kind of dig down into it, you'll find that our reads and our writes are optimal and POSIX-y, if that's a word.
So we're way over time, but this is really fascinating. So maybe let's do another question, and then we can go to the happy hour part. But I do want to sort of keep roughly to that we're like 20 minutes past time right now. So does anyone have a final question that they think is good, or something from the chat? Anyone, just go for it.
I do.
Okay.
Package management. Do you see the evolution of that just building on top of URL imports, and people will end up versioning that, and then that's your package management? Or do you see a role for a new package manager to step in?
I think we're still kind of figuring out. So my idea with this URLs is that the system can have a very simple idea of how to it's very easy to explain to other people and for other systems to kind of interact with this URL view of the world. It's also a web standard. This is how websites work. And so I just kind of like stuck hard with this without really any thought as to how this actually might be used in kind of like larger projects, and in the way that people use npm or cargo. And what has developed is some patterns that I think are pretty interesting and are pretty usable. I'm not sure. I think there's still some kind of open questions, but what people tend to do is they have like a deps.ts folder. And so people don't generally, say you have 10 files in your project. People generally don't put the absolute URLs in every single file. They kind of put those all into a deps file and then re-export the things that they're using from there. And so you end up having one place where you update, and you don't have to update all of your code. So you kind of have this coding. It's essentially a convention for kind of where you lay out your imports. I think the problem that is not solved is kind of the semantic upgrading and kind of diamond dependency problem. So I depend on A and B, and A depends on C version 0.01, and B depends on version, sorry, this is too complicated. B depends on version 0.02, right? So, supposedly what you kind of want is to dedupe that C dependency. If you guys get what I mean by this diamond dependency, where one thing depends on two things, which then, ideally depend on one thing. But you tend to have this kind of fanning out effect because everybody depends on slightly different versions of other things. This is a hard problem to solve. I think in some ways we've solved this by having this standard library. And so, in Node, there's so many little utility functions. And so, you kind of have this really exponential fan out of dependencies. And in Deno, you kind of have a fan out, and then everybody kind of goes back and terminates at the standard library, because the standard library has no external dependencies. It implements a bunch of the left pad or whatever the hell. And so this all kind of is less of a problem in our system. But we still have the problem where I depend on the standard library version 69, and you depend on the standard library version 70. And so you end up having duplicated code in your dependency tree. This could potentially be alleviated at the server level by doing kind of semantic version redirects or something. So imagine you link to version 0.70.0, it could redirect you to version 0.70.1 if such a thing came out. But yeah, this is getting a little complicated, and anyway, I'm not sure if extra tooling is available. It seems like people are able to build pretty complex programs with the system that we currently have, and it's pretty simple, which is nice. And maybe that's actually worthwhile. Just like whatever, it's modules or URLs. Let's not add anything else, and that ends up being kind of nice. But yeah, very, very potentially, like some tooling might emerge to kind of handle this in some better way.
Super cool. Well, I wish we could keep going, but we got to go to the next part of the event. Sorry to everyone for being over time, but this has been really amazing. So what we're going to do now is we're going to do social happy hour. And the way it works is we're all going to join a thing called speakeasy.co, and we're going to hang out. So it's speakers and attendees are all going to join, and you're going to be matched to a random attendee for a 5-minute chat. And you're going to be given like a fun sort of conversation starter question that you can use if you don't know what to talk about. Feel free to ignore it if you have a question in mind. And this is a chance for the attendees to hopefully you get matched with a speaker. If you have a burning question, this is your chance to ask Rod or Ryan whatever is on your mind. And we'll probably just hang out there for the next 30 minutes or so, and hang out and chat. So that's the URL there on the screen, speakeasy.co/JS. So we're going to go over there in another minute. Does anyone else have anything final to say?
Thanks, Ryan. That was really cool talk.
Thanks.
Yeah.
For having me.
Thank you.
It's fun.
Yeah. Thanks everybody for coming. Thanks to the panelists for being part of it, and we'll see y'all over at the Speakeasy for the happy hour. Okay. See ya.
Yeah.